We've all heard of the discovery of the Higgs, and it's called repeatedly in the media the God particle. And it has proven in my speaking around Europe to be a very attractive subject for people today, especially because it's called the God particle. So that it gives us a natural way to raise theological issues. So this is the backdrop to today's workshop is scientific apologetics, or apologetics on scientific questions, which is all that scientific apologetics says. It's not a special approach. So I want to start with, I need to give you a segment of science, which is tailored to people who don't know too much about it. In the questions and answers, I'd appreciate if I could kind of rush through this, because I want to have discussion about this, and you can ask questions about the beginning part if you don't get it. There's a standard model by now of particle physics. It's called the standard model, just like there's a standard model of cosmology and actually a standard model of the origin of light. But it all kind of, I think of it as starting in 2005 when Thomson discovered the electron. And then during the last century, physicists found a total of 12 elementary particles. Each one had an antiparticle. That came mid-century when Dirac relativized the quantum mechanical equations and was forced to, this has already actually been covered in a previous talk, was forced to confront the presence of the possibility of what were called negative energy solutions. He thought he made a mistake in the mathematics, missing a wonderful opportunity to tell people, go look for the positron, which is the electron's antiparticle. Now, antiparticles and particles eat each other up into other forms of energy and mass. That's why they're called anti. The positron, the anti-electron, is exactly like an electron. When it eats an electron up, or an electron eats it up, when they eat each other up, they form a little atom called positronium. Where the electron doesn't go around the proton like in hydrogen. They go around a common center of mass because they have equal mass. They drop down into the ground state, and then they explode within a microsecond into 2 or more photons. And it's a kind of an exercise in elementary introductory particle or modern physics to have students tell us why, if there are 2, why they have to come out in exactly opposite directions with the same energy. And if there are 3, they have to be coplanar. And those are some of the principles we were trying to teach at the early stage. So that just gives you an idea of what is an antiparticle. It has the opposite charge, but if the particle has 0 charge, then it has 0 charge. But it has the opposite charge and pretty much all the same other properties, except for certain quantum numbers that become their negatives when you have an antiparticle. So in addition to gravity, electromagnetism, and strong nuclear forces to hold nuclei together, physicists found a weak force which gives rise to so-called beta decay. It occurs between quarks and lepton particles, I'll define that in just a minute, that cause weak nuclear decay. If you've had some kind of radioactive imaging, like stress treadmill or something like that, it's possible that they use a beta decaying nucleus as the isotope. It's also possible that they use one that emits gamma rays, but it all depends on the particular medical experiment or test that's being done. So basically 4 forces now instead of only 3. There's 2 types of nuclear force. One is strong, one is very weak, but not as weak as gravity. And the matter of quarks has to do with the discovery that protons and neutrons were not elementary particles, but were composite particles, had subsets. And the search is always to find the irreducible particles, the so-called elementary particles. The weak force is produced by means of three massive particles called the W plus, the W minus, and the Z0. My thesis was about the W plus and minus. It was in 64. They weren't discovered till 83. Experimentally, we were proposing ways to observe them in atoms, their effects in atoms if they existed. It always has to happen that they find them actually in experiments, and they did later on. But what does the standard model look like? Well, there are four forces, and each force is mediated by a particle. Electromagnetism is the photon. That force gets produced by an exchange of photons. So if two particles are, I'll show you a picture in a minute of how that happens. So the particles are, for the strong nuclear force, the force is actually occurring between what are called quarks, subsets. The elementary particles compositely making up the proton, the neutron, and all the other strongly interacting particles. And those quarks interact with each other by means of a thing called the gluon, from the English word glue. You run out of names after a while, or physicists have a certain fanciful delight in naming things like charm and flavor and beauty, and I mean, seriously, there are quantum numbers that have those names. So the strong nuclear force is mediated between quarks by this gluon. It has spin 1. That means it acts like it's spinning, like it has angular momentum, and it has zero mass. The electromagnetic force is mediated by the photon, which has spin 1 and zero mass. You start to see a pattern emerge. The weak nuclear force is mediated by three particles. The W plus and minus are actually each other's antiparticles. And the Z0 is neutral. Each of the others have the same charge as the electron, but they're one's plus and one's minus. They're very heavy, 80 and 91 proton masses, for 80 for the W's and 91 for the Z0. And then there's gravity. And we particle theorists believe that there is a thing called the graviton that mediates the gravitational force. For theoretical reasons, it would have to have spin 2, not 1, and zero mass. So we have sort of three, but we haven't found it, so we're still looking. Experiments are going on right now to try to find the graviton, but it's going to be tricky, and it's going to take a while. So here's how it looks. These are the building blocks, the Lego set, the block set out of which everything seems to be built. Someday the story may include new members. I don't know, but at least as far as we know, this is it. There are the quarks are 6 in number. Yeah, as a laser, you're good. The neutron and the proton are made up of these two, up and down. Here's charm. Here's strange. Top, bottom. I mean, it's kind of interesting how they get named. These three quarks were discovered first, and then some of these other ones were filled in. The bottom quark wasn't discovered until recently because it is so, the top, because it's so heavy. It's basically 170 or so proton masses. It's a really very heavy thing, and you have to provide all that energy in a collision to see it. And you will, and by the way, you can never see quarks. They never come free. And that's a subtlety. If anyone's interested, you can ask me later. But we know they're there now. And someday there's even a hope that there might be a way to see one separate by itself. But most of the time, that's not going to be possible. Okay, so here are the, wait a minute. Here are the mediators of the forces. These are the so-called leptons, which from the Greek word leptos, which is weak. They experience the weak nuclear force, but of course the electron and the neutron, the electron experiences electrical force, but its neutrino does not. The neutrino appears to have a very small mass, if any, but it probably does have a small mass and no charge. And it's very elusive, it's very difficult. The mean free path of a neutrino in lead, the mean free path before it hits anything, 100 light years. Very hard to observe, but they have been observed in beams of neutrinos have been produced. So these particles are considered elementary, and the quarks make up 6 elementary particles. Not all of them are stable. The up and the down are. Some of the other ones can make decays into other members of this set. The mu is a heavy electron and can decay into the electron, and does. And it has its own neutrino, and the tau is a third particle with the same properties except for mass and its own neutrino. This is called 3 generations. For those of us that are believers, there's this beautiful sort of symmetry in the repeated theme, and notice the threefoldness of it. It's interesting. I mean, you begin to wonder, what's this about, really, if you're a believing Christian. So that will pretty well cover, and I'll show you how some of this works. All of nuclear physics basically can be understood by the highlighted boxes that I've just shown. The up, the down, the electron, its neutrino, and the W. That pretty much covers the whole phenomenology associated with nuclear physics and electromagnetism and electron interactions and so forth. The proton looks like this. It's an up and a down. Notice a strange third integral charge. This is 2/3 of the electron charge. This is minus 1/3. So the math goes 2/3 plus 2/3 minus 1/3. There it is, the positive value of the electron charge. 1e instead of minus e, which is the electron charge. The neutron itself is, and the antiproton would be made up of 2 anti-U quarks and 1 anti-D quark. It would have charge -1. The pi plus meson, which used to be believed to be the mediator of the nuclear force, is in fact made up of 2 quarks, an up and an anti-down. An up has 2/3, an anti-down would have plus 1/3. So 2/3 plus 1/3 is 1. Pi plus meson. 1 electron charge, positive. The neutron itself would be UDD. The up is 2/3, and 2 times minus 1/3 is minus 2/3, so you get 0. Neutron has 0 charge. So you see the building block just works like this. And those little numbers there are called quantum numbers, and they're mostly additive as you look at the composites. So how do we understand, and the electron is elementary and its neutrino is elementary. So here would be what we call a Fineman diagram describing the collision of a neutron and a proton in the old days by the strong force. They would exchange a pi minus here. The neutron would change into a proton. The proton would change into a neutron. And that momentum transfer of the exchange would give rise to a force between the two. Do you get the idea? And all the different phenomena of binding and so forth can be worked out in terms of these kind of diagrams, but these are the ways that we picture the basic interactions that are going on, these so-called Fineman diagrams. And they have a direct mathematical meaning in the mathematics. They come out of the mathematics. So a neutron here does just what I said. I already said that, so I don't need to repeat it. Now here's a Fineman diagram for the proton-neutron scattering when there are quarks. Here comes the proton with an up. I guess this kind of goes from the bottom here. Here's 2 ups and a down, and here's 2 downs and an up. And what happens is that one of the quarks comes over from the neutron into the proton, and one of the quarks comes over from the proton into, I guess, for technical reasons, the arrows run backward there, but the thing really is going like this. the gluon, you see, is acting between quarks here and here. This is the gluon. And here again it is. So this is equivalent to this diagram that we just thought about, because the U bar and the D make up the pi minus meson. So you see, it's really the old picture isn't wrong. It's just that the thing that gets exchanged is the composite of two quarks. Interesting, isn't it? Interesting pattern, the way the Lord made the world. The quarks can exchange both neutral massless gluons and individual quarks also. That is, they can move from one composite to another. Now, here's simple electron scattering, where two electrons they would repel each other, so the picture is actually physically correct in that way. Electron scatters off another electron by means of the force. Both electrons change their momentum by exchanging this photon. Okay, what about nuclear beta decay, in which usually a neutron changes into a proton, emitting an electron and a neutrino, or a proton changes into a neutron, emitting a positron and an antineutrino. Sorry, the other way around. The first one was the antineutrino. This one would be the neutrino. So that's the most basic weak interaction, beta decay. The neutron changes into a proton, a negative electron, which balances the charge, and a neutrino, antineutrino. How does that look in the quark picture? This D, one of the D's for the neutron, changes into an up by interaction with the W minus, which carries off a negative charge, leaving a positive charge behind for the U. To go from D to U, it takes +1. So here's the W being exchanged. And it decays into an antineutrino and an electron. You see how it goes? So it becomes the force mediator for this type of weak nuclear force leading to this decay. Or pi decay. Particles always keep changing according to the rules until they get to the lowest energy state, until they get to one of the stable ones. So the pi plus starts to cascade down, and it's heavier than the mu, but the mu itself is unstable because it's heavier than the electron. So this pi plus can actually turn into either a mu plus and its neutrino, or an electron plus, a positron, plus its neutrino. And the diagram looks similar. There's a U and a D bar coming in, annihilating each other. They're particle and antiparticle, not of each other, but the difference in charge is 1, and they go into a W, and then that decays into the mu plus and the new mu. Or it can go directly into an E plus and a new E. So do you get the idea kind of how the building blocks start to work together to form the phenomenon that we observe? Because when you have a radioactive nucleus, you see either the mu and the nu come up, but more typically for nuclei, a positron and a neutrino, or an electron and an antineutrino will come out. You won't see the neutrino. You'll see the electron. That's what would image or cause, because that neutrino is going to go a long way before anything happens to it. So to get quickly to the Higgs issue, I want to talk about grand unified theories and why they're needed. But think of the first three quarks that I highlighted, the up, the down, and the strange quark. Those three form if you mix them up, if you take a so-called linear combination of them and then an independent linear combination and a third independent linear combination, it's kind of like making three different new quarks. And if the theory wouldn't change when you did that, it's called invariant. And then the group of matrices that allow you to mix them, because it's just a 3x3 matrix that you write down when you do that. 3x3 matrix. And if that matrix has a certain property called unitarity, which is simple to state, meaning that the matrix times its Hermitian conjugate is the unity matrix, then it's called a group SU3. Actually, you need one more condition for the S. But that becomes a group mathematically. It's a structure called a group in mathematics. So we would say if that kind of mixture could not change the physics, we would say that SU3 is a symmetry group for the theory, for nature. And it appears that that's the case, almost. I could inject a theological point here, which I wouldn't do if I were given this lecture apologetically in most venues. Although I would if I were in a Catholic university, which I feel more freedom to talk about implications. One of the themes that keeps emerging in physics and is very much at the center of this subject is what we would call spontaneously broken symmetry. It seems like behind the nature there's symmetries, beautiful symmetries, simplicities. But they always get broken spontaneously. Almost like every leaf on a tree has the same DNA, barring a few mutations here and there. And yet each leaf is a different shape. No two leaves are the same. And so you have a symmetry in the DNA, but you have a broken symmetry in the actual shapes of the leaves. And life gets interesting only through broken symmetries. The most obvious broken symmetry is male and female. I mean, we're all made in God's image, but there's a certain differentiation between us. So, and it seems to show up in physics, not only in threefold, but because I'm about to show you a broken symmetry. To a zeroth approximation, any mixture of three of these quarks using these unitary matrices would give three new quarks, and that would not change the theory to a zeroth approximation. At real high energies, for instance, you see this sort of symmetry showing up. But there are actually 8 particles to which the proton and the neutron behave. And speaking mathematically, they form the 8-fold representation of the group SU3. That's the mathematics. There are 8 of them, and they can be represented by a matrix, and those 8 by 8 matrices form also a representation of the group. So anyway, they're the proton, the neutron, the lambda 0, the sigma plus, the sigma 0, the sigma minus, the psi minus, and the psi 0. They have different masses. Only the proton is stable. Every other one is unstable. They have the following quark contents. It's not too important, but you see you have to add the strange one because some of these are so-called have this property of strangeness. So they have the strange quark in there. But notice there are no antiquarks here. There is an octet of antiparticles too that go with each of these. So supersymmetry in the Higgs. So gravity is a weak force. It's not yet included, as I said. The exchange of the intermediate vector bosons, as they're called. Boson just means integral spin as opposed to half integral spin. Any object that has half integral spin in nature is called a fermion, and anyone that has an integral spin is called a boson. So the words meson and boson are pretty much interchangeable. Electromagnetism comes from photon exchange. It's stronger yet. The gluon is stronger yet. But for high energy forces, collisions, these 3 forces seem to have the same strength, and all the masses appear to become 0. And it's called supersymmetry. Here's a chart of what we expect. Now these are hugely high energies, and we haven't gotten here yet, but that's why they're building bigger accelerators. But they've already seen this tendency to converge in the strength of the force. So you're getting to a place where there's only one strength of 3 forces. Each of 3 forces has the same strength in dimensionless form, and all the masses of those particles become 0. That's this sort of latent symmetry behind all of nature, is excluding gravity, which is another matter that we're still trying to integrate theoretically and experimentally. So a theory that starts by writing down the defining equation called the Lagrangian out of the fields. You take the fields for each of the particles. Each particle has a field operator, and you put them together in certain really neat ways according to certain invariance principles. And you get a simple function of a type first introduced by Lagrange, called a Lagrangian. It's no longer made out of simple functions like Lagrange made it up. It's made out of operators on a Hilbert space that form a Lie algebra, et cetera, but it's still a Lagrangian. And that Lagrangian has this full symmetry in it. But the actual particles I showed you in that first picture have widely different masses and widely different strengths of forces for the three forces. So at low energy, the world breaks the symmetry. Now, how can you have a ground state or a low energy state that doesn't exhibit the symmetry coming from a theory that does exhibit the symmetry? That's the whole deal here. It's called spontaneously broken symmetry, because if your defining equations have a certain symmetry, then the answer should have the same symmetry. Why should the lowest energy state break the symmetry? Well, the why is something that the Lord may tell us someday, but we're not going to find it out by science. But really, it's how. How does the symmetry get broken? So I think this is really beautiful mathematics, and maybe Andy will talk about it later this afternoon. Spontaneously broken symmetry. A magnet breaks the symmetry. The laws of magnetism are parity invariant. They look the same in a mirror. But a magnet doesn't. It's got a direction. And it's the lowest energy state of that particular piece of iron. So it represents a spontaneously broken symmetry. And that one was solved first by the introduction of a thing called a Goldstone boson into the equations. A Goldstone spin integral particle. And then there was a model field theory called the Yang-Mills theory, which also had a spontaneously broken symmetry in it, and it was also obtained, I mean, by the introduction of a Goldstone boson. And there's a technique that's been worked out to do that introduction. It's purely mathematical, and you just carry it out a certain way, and you get the spontaneous breaking of the symmetry for the lowest energy state. But you have to add a term to the Lagrangian. You have to add something to the Lagrangian. So yeah, this is just saying what I said. I mean, it just lists all the ways that you're going to have to break the symmetry. How can this be? So I mentioned ferromagnetism, and I mentioned particle theories that could be solved, one of which is the Yang-Mills theory. It's a simple field theory just to play with mathematically, to learn how to deal with field theories. And the problem is that these particle theories in particular gave infinity for answers if they didn't add an extra spin zero particle. And they also did not show the broken symmetry. So the Higgs boson comes to the rescue by being the extra term in the equation that allows the spontaneously broken symmetry to happen, and also, interestingly, cancels the infinities. Now, the philosophical part of this will come in just a minute, because there's some important philosophical issues here that are apologetically useful. But I'm taking a risk trying to do this, because this is almost as bad as biology to try to explain to people. But the biologists are better at picturing it somehow. So this Goldstone boson was proposed in 1964, right when I was getting my PhD, by Peter Higgs and actually 5 other people too. And the standard model with the Higgs showed spontaneous symmetry breaking. Infinite answers disappeared. We have a special term for that. We say that the theory becomes renormalizable. That's a technical term. It means that infinite answers go away. Infinity is not a good thing to get for an answer to a calculation. The lowest energy state, particles at rest, had masses with the Higgs in place. The lowest energy state had 3 different force strengths in the right order in that once you added the Higgs. So you see, it begins to have exactly the right characteristics for the correct broken symmetry for the world as we see it. 48 years the search went on. They built a Large Hadron Collider to do it. But in Discover magazine, when they were explaining the building of the LHC, its goal was at once simple and grandiose. It was created to discover new particles. One of the most sought of these, the Higgs, also known as the God particle, because according to current theory, notice this sentence, it endowed all other particles with mass. Now, if you found the first part of my talk boring, that should wake you up, because it is boring. It's all a matter of following the dictates of technical mathematics, right? And you do what you have to do to make the mathematics work and agree with nature. And every principle that you've discovered that they must obey. You're guided by mathematical consistency and data. Why should that type of an endeavor get us this deep into understanding what's going on? Why should mathematics work? You know, I'll mention this a little in just a couple minutes, but I don't have a lot of couple minutes left, so I want to keep going on to the more philosophical part. The Tevatron near my home in Chicago probably saw a few of these Higgs. That machine had too low of an event rate in its expected mass range, so they built the LHC, and you can see how complicated. I mean, those little guys start out, the protons, they start out here, they're only up to 3/10 the speed of light by here, and 8/10 by, 7/8 by here, and 0.999999, whatever that is, C by this point up here. They're almost going at the speed of light. It's designed for high energy, and they saw it in 2012. They finally got enough events to... what? I'll talk, yeah. At these energies, when two protons collide, many particles are produced. That's 1,000 proton masses. A TeV is 1,000 proton masses. So you can produce anything on the list and more by that collision. And these complex detectors are incredible engineering marvels. They look at billions of collisions per second. You have to find the key ones that occur maybe once per day or a few times. So this would give a typical event. It's just a huge spray of particles, and you got to sort it out. So you better believe that every advance in electronic technology and computers and sensors and all the rest are necessary to even sift through that splash of particles that comes out. And I thought it's interesting to see a picture of one of the main detectors. There were really two big ones, ATLAS, ATLAS, and CMS. And here's a person standing there. That's a particle detector. And it's jam-packed with very expensive, one-of-a-kind electronics. Well, they found it. 10 billion, 14 years, 10 billion US dollars. 1,000 physicists. They announced it. 5 standard deviations above the background in July of 12. And the level of significance of 5 standard deviations is considered scientific proof that a particle that was probably the Higgs was found, but there were problems with the relative probability of it falling apart into different objects. That's called branching ratio. So, here's one set of objects, here's another. You have to be able to predict the relative frequency. And that was predicted, but it wasn't really quite coming out right. But now, in March of this year, they said it's okay. We're getting the right branching ratios. It's for sure. So that's been verified very firmly as of March of this year. Wisconsin physicists. I got my PhD at the University of Wisconsin. And A month or two ago, I got a copy of our physics department newsletter. They have some high energy experimentalists in our department, and they were working on both the ATLAS and CMS experiments, some of them on each one. And here's the Higgs at around 125 in these units of so-called GeV over c squared. I think of a GeV over c squared as a proton mass, the mass energy in a proton. So you see it's a big bump on an otherwise fairly smooth curve. And that's how these highly unstable particles show up. They show up as, it's like the pieces that come out want to be together at a certain energy. So they hang together more often than not. And that mass becomes the mass of this unstable particle that's very rapidly decaying. In quantum mechanics, the so-called width of the distribution and the lifetime are immediately related by the uncertainty principle. So that's one way you find the lifetime is by the narrowness of this peak. And here's the other experiment. So this is the data from the other one. So I just put that in because of a little narcissism on my part. Why take it from some source besides my own physics department newsletter? So here's the picture now. We have a Higgs. But interestingly, when you put the Higgs in, the way you have to do it according to Goldstone's methodology to be consistent with everything, you end up involving these two particles, these bosons also. And this step gives mass to those bosons. That is, they result in a mass term in the Lagrangian for those particles. Is that giving mass? That without the Higgs, there's no mass term because you had the full symmetry built in, but now that you have the Higgs, a term shows up that corresponds to the term you would put in if the particle had a mass. It emerges from the calculation. And then the interactions of the Higgs give rise to all the other, wait a second. The interaction of the Higgs gives rise to all the other masses. So, how did it get called the God particle? Letterman wrote a book by that title and subtitled in a modest way, If the Universe is the Answer, What is the Question? It's a modest. What it is a very narcissistic autobiography of his days in particle physics, is what it is. But, you know, you dress things up. In the first chapter, he says, because the Higgs was so hard to detect, he wanted to title the book, now I apologize for this, but this is what he says in the text. He wanted to call the book That Goddamn Particle. Now that shows an attitude, a realistic attitude. Hard to find, mathematically abstruse. It's a term of being upset, you know, of being angry at something. And Houghton Mifflin didn't think they wanted to market a book with that title. So they negotiated, and they came up with the title for the book, The God Particle. Most people don't know that part of the story, but I got the book out of the library in my little town, and I started to read it. And he has some other interesting things to say about the what I would call the creation myth of materialism, the whole Big Bang thing. He considers it much more tentative than you're hearing in the press. This is Letterman. He won a Nobel Prize for his own work in experimental physics, particle physics. So the media has taken its name and given it a mystical and spiritual emphasis. It sells books that may reflect Letterman's point of view. It was sensationalized by the clever use of language, which helps to sell books. The hyped up language that's used appeals to people's felt need, I think, for spiritual reality. It produces a materialistic God substitute. And the media mysticism helps to generate public financial support for very expensive experiments, by the way. Because, after all, science these days is selling itself a lot of the times on the basis of the fact that we want to know where we came from and where we're going. And so this kind of language helps people to commit. tax resources and so on to these very expensive endeavors. So, however, well, this is the British Daily Mail. Atom Smasher reveals Higgs boson, the key to the universe. Ooh, wow. Huh?
It must be true.
Yeah. Well, that's one of the less reputable papers, isn't it? Yeah. Yeah. But I mean, they read it out there, Andy. I mean, a lot of people read it. Probably more than read the Telegraph or something, actually. It begins, the God particle, hailed as the holy grail of physics, may have been glimpsed for the first time. This was a little earlier on. Further, the Higgs boson is regarded by those who know about such things as the key to understanding the universe. Its job is apparently to give the particles that make up atoms their mass. Well, I have a lot of stuff here that I'm going to skip over. Some dialogue and blogs and so forth showing a disgust at this approach, but also postmodern attitude toward truth. Dilbert even took notice. The cartoon in US, anyway, quite famous, Dilbert cartoon. First frame, yes, I found the Higgs boson. Here it is, see, in this little apparatus right there. So out comes the voice, build an arc. He switches it off. No Higgs, no God particle. He says nothing but trouble. He gets the Higgs makes a demand on him. After all, if you're the God particle, make a demand. The essence of Christianity is, will it be your will, not my will, or my will, not your will? And this is beautifully understood and represented by the cartoonist in this particular frame cartoon. The comment on it that was online when I took this off is there. It serves as a nice illustration of the confusion when physicists talk this way. They are not using God in the sense of deity, personal deity, liable to add hassles to one's life by issuing awkward commandments. And that actually capsulizes the human condition that we're up against in trying to spread the gospel. So, I mean, right here in the middle of this whole highly scientific subject is the same struggle that goes on everywhere. And I think it's useful to see that. Furthermore, we've used mathematics. Is it really an accident that mathematics unlocks the truth so much? It's like a magic key. You come to door after door after door. You put in even the biologists we've been hearing using a lot of mathematics, they put in the key with mathematics, and the door opens, and you go to the next door. It's the same key, same key, same key, same key. You get to thinking that it's something special about this key. And a guy named Eugene Wigner, who also won a Nobel Prize in theoretical physics. But first I want to comment that the endow word suggests that the laws are being portrayed as an uncaused cause of the universe. And that's a metaphysical thought and not a physical thought. What is the uncaused cause? Is there an infinite chain of cause and effect, and therefore no original cause or uncaused primary cause? Or is there a primary uncaused cause from which all other cause and effect proceeds? When you say that Higgs endows the other particles with mass, you're suggesting an answer to that question. Are they really? Can we describe nature rationally using logical mathematics and experimental observation? Materialism says it just works. We learn to think this way because of evolution. And that I can show you, that being quoted over and over again. I didn't just make that up as someone else's worldview. They stated it as their worldview. The unexplained is this marvelous match. And Wigner wrote an article called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. You want a prestigious peer-reviewed journal, just think about Communications in Pure and Applied Mathematics, pages 1 through 14 in the volume for 1960. That is what we would call a prestigious journal, article. They're giving it the greatest honor. It's not just because it's Wigner, because this talk was also given at the Cron Institute in New York. So he says 12 times in the article that there's a miracle. Something bordering on the mysterious in the natural sciences. He says there is no, he's an agnostic at best. No rational explanation. By the way, I did a fair amount of research to make that statement of his writings and so forth. I tried to understand his worldview framework. And at best, he's an agnostic, but I wouldn't call him a new atheist, kind of not evangelist. He uses the word miracle 12 times in the article. He asks us to be thankful or express gratitude 4 times. His materialism has no causal agent to do the miracle or to receive the gratitude. Feynman, you've heard of him. Fineman Diagrams. The fact that there are rules at all to be checked is a kind of miracle. That it is possible to find a rule, like the inverse square law of gravity, is some sort of miracle. It is not understood at all, but it leads to the possibility of prediction, that means it tells you what you would expect to happen in an experiment you have not yet done. And I have a further quote from Einstein himself, which is a little more ambiguous. Sandage, a Christian, says it's, oh, by the way, in his article, Wigner explicitly says that Darwinian evolution cannot explain this match. It's too indirect. It's too much just a game the human mind plays. It has no immediate survival value. He's very emphatic about that. If you ask him, does he believe in Darwinian evolution, I will bet you he says yes. But he doesn't believe it explains this feature of reality. So we all, Jews, Christians, and Islam, although I'm not that familiar with the subtleties of Islamic theology, we have a personal causal agent who is intelligent, eternal, powerful, and who shared the rationality he used in creation with the human mind. And God made man in his own image. In the image of God, he created them, male and female, he made them. So the logic by which, and mathematics by which his own mind works in some measure is shared with us. And Galileo said that, and others have too. Galileo said God is a mathematician. He understands all theorems. We only understand a few. The ones we understand are just as certain as they are in the mind of God because of their logical necessity. So you see his understanding as he did his science of this connection. Galileo. Interesting thing is that, so for us, the uncaused cause of all is a personal being. And of course, that's the way he announced himself to Moses when Moses was trying to get out of his job, his assignment. And he says, what's your name? I can't go without the name because they'll ask me and I have to be able to tell them. And what does he say? He says, this is not news to anyone in this room, I don't think. But he says, I am who I am. You tell them, I am sent you. That is a direct claim to be the uncaused cause of everything. And Jesus said, in answer to the Pharisees and Sadducees, before Abraham was, I am. And they knew what it meant because they picked up stones to kill him. So, see, for us, the mathematics is there because of the mind of God, which works that way. And notice the beautiful broken symmetry. You ever think of Trinity, 3 in 1? Well, the Trinity is a broken symmetry. Okay. I think I've illustrated here how, well, a materialist says because there is a law of gravity, the universe can and will create itself. That means that the universe is the uncaused cause. We say no, not true. They don't create anything. Laws don't create anything. They describe the behavior of what already exists, and the Higgs field everywhere is not nothing. What I wanted to show you in this, and I'm finishing with this comment, is that as an apologetic tool, well, first of all, we need to understand it ourselves, and we need to see where the flaw comes. We need to see the flaw comes in attributing to a mathematical machine-like construct which only exists moment by moment by the faithful imposition of God, by God, of that structure on the universe. Right here, right now, those laws hold only because God maintains them here, now. And the next moment, and the next moment, and the next moment, same laws. And that's well attested in much scripture about the faithfulness of God's action in the world. So we understand nature, natural world, as an ongoing act of God. In him we live and move and have our being. And this is very key to keeping our feet straight under us in this modern world where science is so important. So what the laws mean is they describe this way that God does these things over and over again, the same faithful way. And I think that it's a very important apologetic tool also to use that to help open people's eyes to their creator, which is the first step in facing their accountability to the creator. Thanks a lot.